Well, welcome back. Today we're going to be discussing a Newton's method example. Recall that Newton's method is a way of finding the roots of a polynomial, or at least approximating the roots of a polynomial or any differentiable function by using an iterative process. So using a formula over and over again to gradually get values that are closer and closer to the value that you are looking for, the value of the root. So today we're going to be looking at a particular example. This one is out of the textbook. It's a rather lengthy example. Page 243, problem number 15. Use Newton's method to estimate all real solutions of the equation x cubed plus x minus 1 equals 0. Make your answers accurate to 6 decimal places. Now remember that Newton's method allows us to rather quickly find an approximate value, and the more iterations we do of Newton's method, the more accurate our result becomes. Just a reminder, the formula for Newton's method tells us how to pick values that are close to the actual root. And our new guess is a modification of our old guess by subtracting the ratio of the function value at the old guess to the derivative of the function at the old guess. In our particular case today, the function we're looking at is this function x cubed plus x minus 1, and f prime of x, the derivative function, will be 3x squared plus 1. Very straightforward polynomial derivative. In terms of starting out a Newton's method problem, we have to come up with the first guess. We have to come up with an initial value for x. And as we saw last time, that choice of initial value can have an impact on how quickly your results converge, how quickly you get to an answer. Especially trying to find the result to 6 decimal places, we want to make sure that we do a good job of choosing our initial guess. Looking at the original polynomial function here, f of x, I would guess that something around 1 would be an acceptable guess. Notice if I plug 1 in for x, we have 1 cubed plus 1 minus 1. That gives us a y value or output of 1, which is fairly close to 0. Obviously, if I pick anything too large, the x cubed will work. 0 would also be an acceptable solution here, right? If I pick 0, then we end up with minus 1. So there are several choices you could make. You could also choose something like a half, right? That's in between 0 and 1, possibly another good choice. So the choice is up to you of how you choose to proceed. I'm going to let our initial guess be 1. I think that will be most useful for us to see here. So we'll go ahead and start by building a table. This is a nice way of keeping track of the outputs of your values here. So we have our old x values, the y values that go along with those, the derivatives at those points, and again, through Newton's method, we use those to compute the new values. So if I'm going to go ahead and get started here, I'm going to choose an initial value, an initial guess here of 1. F of 1, recall, is 1 cubed plus 1 minus 1. That's going to give me an initial output of 1. And the derivative of this function here was right here, 3x squared plus 1. So when x is 1, that's going to give me a value of 4. So here we're going to have 1 minus 1 over 4, or 0.75. is where the tangent line to the curve at this point intercepts the x-axis. So I'm going to go ahead and use that then as my next value, 0.75. You can follow along with your calculator if you want. Eventually you find a nice rhythm to work these problems in. I've gone ahead and worked the problem out to begin with. Here, if you plug 0.75 into f of x, you find that you get out a value of 0.171875. So that's simply taking this value here, our 0.75, and plugging it in to the function to see what we get out. I'm going to do the same thing with 0.75. This time I'm going to take our 0.75 and I'm going to plug it into the derivative function. When I do that, I'm going to get the slope of the tangent line when x equals 0.75. That gives me a value of 2.6875. And if I compute then using Newton's method the new value, that will be this 0.75 minus 0.171875 divided by 2.6875. Okay, so that's what Newton's method gives me as my next guess, and if you work that out, that ends up being a slightly more complicated decimal. That is 0.686047. Okay, and if you feel like you have the hang of this now, what I would encourage you to do right now is to just pause the video and try and go through here and see where your answers are. Go through and do the iterative process here, see where you end up with being accurate to 6 decimal places. And one thing to note is very easy with the powers and things. You really have to watch the entry of things in the calculator. It's very easy to trip things up. I'm going to go ahead and continue now, so if you do want to work through things on your own, maybe pause and come back to check your work. If we plug in 0.686047 into the function, we end up with 0.008942. That's our output. And remember that that's really what we are interested in this problem, is our output here. This is what we're trying to make 0. We're trying to make the function 0. So the closer that these values get to 0 demonstrates that we're getting closer and closer to a root. We're trying to find the x value that makes that true. So as we continue to do this problem, we get closer and closer to the correct answer. If I plug in that x value of 0.686047 in to get the slope, we find the slope is 2.41198, and Newton's method then gives me a value of 0.68234. So notice that those old and new x values are fairly close. We're not changing the function by much here because we're already very close to the root. So 0.68234 becomes our old function value now, our old x value now, and we're going to do the iterative process once again to come up with the value. This time we get a very small number for f of x. We get 0.000028. Again, that should be getting closer and closer to 0, so that's a good sign. The derivative at x equals 0.68234, the value of the derivative of the function is 2.39676. And Newton's method gives us a new x value to try of 0.682328. Notice that that's also very close to the value we had before. So if we go ahead and plug this in, we end up with 0.682328, and evaluating the function at that x value gives me a very small value, 0.000001. Okay, and in fact, this is, with the settings I had on my calculator, this is the smallest value that it could record other than 0. The derivative at that x value of 0.682328 is 2.39671, and that gives me a new value, a new x value of 0.682328. And if you notice, these particular values are identical. These are equal values. So to 6 decimal places, Newton's method doesn't give me anything different than that. If I were to try and use the iterative process here again, I would end up with exactly the same thing. Now, some of your numbers may look different if you have your calculator settings a little bit different. Don't let that bother you. It's simply a difference in calculators. So the answer here is that x cubed plus x minus 1 has a root to within 6 decimal places. X equals 0.682328, and you can verify that by doing something graphical with your calculator. You can graph that function and look for a root. Recall back in pre-calculus days how difficult it was to find a root. Newton's method is long and tedious, but it's a straightforward process that always gives us an answer as long as we choose initial guesses that are correct and we have well-behaved functions. So this is progress, even though it seems like a very difficult technique to use. So with that, I'm going to ask you to go ahead and practice a few problems. Please bring your questions to class, and I look forward to seeing you then.